Okay, sir.
Well, till last day we had talked about the laws of motion. We had done a lot of numericals on that. And now we are going to go forward and discuss with the topic called gravitation. Now, when I talk about gravitation, I need to tell you that gravitation is something which is related to force, the same force that we have studied in force and laws of motion. When we talk about force, we say that there are mainly two different types of forces, isn't it? One, the contact force, and the second one, the non-contact forces. When we are talking about forces, again over there we had talked about three broad distinctions. We have talked about electrostatic force, magnetic force, and gravitational force. Well, this chapter is dedicated to the study of gravitational force. In this chapter, what we are going to do is we're going to talk about the basic things about gravitation, and then we'll build up from there. We also would be talking about flotation in the next chapter. We'll be talking about buoyancy, but over here, we'll be trying to focus ourselves on gravitation only. If you look around with your NCRT book, you would find in your NCRT book, this is one complete chapter. But if you check out with your reference book, it will be divided into two different chapters, gravitation and flotation. So we'll be going that way itself. We'll start off with gravitation. When we talk about gravitation, it reminds me of a very famous story that every topic of gravitation start with. It was Sir Isaac Newton. We were sitting in a park and he found that an apple fall down from a tree. When the apple fell, he took the apple and started thinking, why did it come down? And that's how the concept of gravitation came into being. He started doing a research on that, and at the end of the day he came up with certain theories related to gravitation. Well, let me tell you very categorically over here, gravitational force is that third category of contact force that I had just discussed. So a force is always necessary to produce a motion in a body. Without a force being applied externally, a body cannot be brought into motion. In fact, if you remember, this is what we have talked about in the first law of motion also, where they talk about the external unbalanced force to move out of the state of inertia. A force is always necessary to produce motion in a body. And that's what we find when we drop a ball from a particular height, or maybe a stone, or maybe for that reason any other object. When we release it from a height, we find that it always comes downwards. Has it ever happened with you that it went upwards? No, never. Similarly, if I throw something upward, you will find that after reaching a particular height, it turns back and moves towards the ground. Well, when it is thrown up, the force with which you are throwing it up will take it to a particular distance, and the final velocity will go on decreasing. In fact, there will be deceleration in the body till the time it reaches the zenith. Once it reaches over there, the final velocity becomes zero. And once it becomes zero, it takes a turn and moves towards the earth under the influence of the force of gravity. This is what we need to discuss in this chapter. But before we start doing anything, we'll talk about the universal law of gravitation as it was put forward by Sir Isaac Newton. Can you see this apple tree? Or maybe the rain? Or maybe the flowing water in the rivers? All are moving in the same direction downward. And that's because of the force of gravity. The earth attracts all the objects towards its center. So we may say that the force with which a body is pulled towards the center of the earth is known as gravitational force, or the force of gravity, or the gravity of the earth. So what should I say if I am asked about the definition of the force of gravity? We can say it is the force with which a body is attracted towards the center of the earth is known as force of gravity. The gravitational force of earth is something which is only acting in one direction. If you talk about electrostatic force or maybe magnetic force, if you remember, we had said that in electrostatic force, there are positive and negative forces when we are talking about because of the existence of positive and negative charges. When we talk about the magnetic force, we did talk about over there at two different types of forces also existing over there, the attractive and the repulsive. But in case of gravitation, we see that all the bodies are attracted towards the center of the earth. It is not the other way around. So there is only one kind of force which is acting, and that too the direction of towards the center of the earth. So the gravitational force of the earth is responsible for what? There are so many phenomena that happen around us is because of the force of gravity. In fact, the atmosphere that we have above us, which makes the existence of life possible on the surface of earth, it's also because of gravity. If you talk about the high tides and low tides that comes up in the oceans, it's also because of this gravitational force. When we talk about the flowing of the rivers, or we talk about the rain falling, or it may be throwing of a stone, all these are attracted towards the center of the earth, or it comes downhill, simply because it's the force of gravity that exists over here. As I promised, I'll talk about the universal law of gravitation and go forward from there. Now, what is universal law of gravitation? Can you see that on the screen? On the screen, you would be finding figure number 4. In figure number 4, you find that there are two bodies over here. One of this is A, the other one is B. So we have two bodies, A and B, and the masses are M1 and M2 respectively. What is it? M1 and M2 respectively. Let me highlight this so that it becomes more clear. Can you see this? Body A and body B. You see, these two are the bodies that I'm referring to, which is having the mass M1 and M2. Now, these two bodies are separated by a distance of r meters between them. What is it? They are separated by a distance r meter between them. When I say r meter, that is the distance between the centers of these two bodies. If I at all consider them to be spherical, in fact, if you see the figure, they are spherical. But this is something which is applicable universally. It is applicable for all kinds of bodies of all kinds of shapes. But then again, why we take a spherical shape? Because Earth is presumed to be a sphere, though it's geoid in shape, but we presume it to be sphere for simplicity of calculation. So, what does the universal law of gravitation say? It says that any two bodies in the surface of the or the surface of the earth, or maybe in the universe, they will be attracted towards each other. I'm talking about this body A and this body B. They will be attracted towards each other with a force which is directly proportional to the product of the masses between them. Which masses? M1 and M2 in this case. It is M1 and M2 in this case. So everybody in this universe will be attracted towards each other, or for that reason, every other body with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So when I say product of the masses, I'm talking about M1 and M2. It would be, the force would be directly proportional to M1 and M2's product, M1 into M2. So as the mass increases of the bodies or the mass decreases, the force changes accordingly. And because they are directly, it is directly proportional to the product of the masses. And if you check, it says that it is inversely proportional to the square of the distance between them. So when we say it is inversely proportional to the square of the distance, we mean that as the distance increases, the force of attraction decreases. And when the distance between the two bodies decreases, the force of attraction increases, and it is following the inverse square law. Now what do we mean by that? Check over here, point number 1, which is an explanation of this. It says that when two bodies are having masses m1 and m2, then the force is directly proportional to m1 into m2. Is that clear? M1 into M2. And if you check over here, the force between two bodies is inversely proportional to the square of the distance between them. So this will be following the inverse square law. What is that? We'll try to explain you right now over here. If you check over here, it is F proportional to 1 by r square. What is it? F proportional to 1 by r square. Now let us presume if the distance between the two bodies, by the way, it's not the radius. We might make a mistake thinking r to be radius. In that case, you can always take it to be d. Well, my dear students, these are variables that are used. If you define it correctly, you can use any variable. There is no problem with that. So rather than getting confused, if you are using m1 m2 by d square, that's perfectly fine. But then you need to define what is d, right? So the distance between the two bodies is the center of the two bodies is r. So if this distance increases, what would happen? You would find that the force will become 1/4. Why? Because r becomes 2 times, means r square turns out to be 4 times, and it's inversely proportional. Check with this equation number 2. You would find since it is double, the decreases force decreases. And if the distance between the bodies is half, means r becomes 1 by 4. 1 by 2 square is 1 by 4. I hope you have been able to make you understand this. 1 by 4. Now this 4 of the denominator goes to the numerator and it becomes 4 times. So the force increases by 4 times if the distance between the two bodies is half. In fact, if you check over here, if I combine these two, it would look something like this. It would look something like this. What do you find over here? I find that F is proportional to m1 m2 by r square. Well, my dear students, I'm pretty sure that you are aware that if I need to remove this sign of proportionality, what I need to do? I need to introduce a constant of proportionality. In this case, the constant of proportionality is G. In this case, the constant of proportionality is G, and it is known as the universal gravitational constant. What is it known as? It is known as universal gravitational constant. This G is having a value which is given by 6.67 into 10 to the power minus 11. We'll calculate it and try to find out the unit what it is. If you check over here, you would find F is equal to G m1 m2 by r square. If it is G m1 m2 by r square, if I need to make G the subject, it would be G is equal to F into R square by M1, M2. Check over here. It turns into G is equal to F into this R goes down and gets multiplied, cross multiplication, it becomes F into R square by M1 into M2. Now we all are aware the unit, the SI unit of force is Newton. The SI unit of force is Newton. So if the SI unit of force is Newton, if the SI unit of distance is meter and the SI unit of mass is kg, so we can say that the unit, the SI unit of the component G, the universal gravitational constant, is nothing but it is Newton meter square by kilogram square. Newton meter square by kilogram square. We can say Newton meter square kg to the power minus 2. Whichever you are comfortable with, you can actually put it in that form. Newton meter square kg to the power minus 2 or Newton meter square per kg square. Did you get that? I was just trying to talk about the unit of the magnitude of G. To find the magnitude of G, what we need to do? Suppose the mass of the two bodies is 1 kg each. The mass M1 and M2 both are taken to be 1 kg. This is just for the simplicity of calculation and trying to find out the value. Both the masses are taken to be M1 and M2 to be 1 kg. The distance between the two bodies is taken to be 1 meter. The distance between the two bodies is taken to be 1 meter. So if I put all these values over there, we would find, let's check with this formula and explain it once again. The formula was F is equal to G M1 M2 by R square. If the masses are taken to be 1 into 1, that's 1 kg each, and the distance is taken to be 1 meter as well, so we would get F is equal to G, because this entire portion would become what? The entire portion would turn into 1 only. So F is equal to G. This is a special case when the masses of the bodies are taken to be 1 kg and that of the distance between the two bodies is taken to be 1 meter. It is calculated and found experimentally. The value comes out to be 6.67 into 10 to the power minus 11 Newton meter square per kg square. Newton meter square per kg square. In fact, there are a lot of numericals that are related to this, which which can come in the exam as well. So we need to be very conversant with these calculations. The only thing that we need to be very very cautious about is the powers of 10, because what we find, the exponential powers, they at times because of our unfocused effort, we get it wrong. Otherwise, these numericals are like cakewalk. What do we find? The gravitational constant G is numerically equal to the force of gravitation which exists between the two bodies if they are of unit masses and they are kept at a distance of what? Distance of 1 meter, that is unit distance. The value of universal constant, as I have discussed, I reiterate once again, it is 6.67 into 10 to the power minus 11. Mind it, my dear students, at times, we tend to make a mistake over here thinking that, oh, since it is something related to gravity, it must be huge. No, it's not plus 11. I repeat once again, it's not plus 11, it's minus 11. 6.67 into 10 to the power minus 11 Newton meter square per kg square. Well, this is what we need to talk about over here. Let's see how to calculate the value. How did we actually reach over here? If you check over here, you would be finding, yeah, I can see people are raising hands. Just hold on for a moment. Let me complete with this discussion and surely I'll take up your questions. You see over here, for the timing, you can lower your hand, no problem. F is equal to G M1 M2 by R square. Now check over here. If I find that my value of G is something which is 6.67 into 10 to the power minus 11. The mass of the body is taken to be 1 kg each. For both the bodies, it's 1 kg each. And for the distance, if I take it to be 1 meter, we find that the force that exists between the two bodies is nothing but 6.67 into 10 to the power minus 11 newtons. I believe till this point it is clear, because this is something which we are just putting in the values over there in the formula and trying to, make the calculations. We find that if the body is of 1 kg each, if the distance between the two bodies is of 1 meter, then the force that exists between the two bodies is 6.67 into 10 to the power minus 11 newtons. And this is a force with which all bodies are, pulling each other. All the bodies are pulling each other with the same force. There are times when people tend to ask me, if it is so, according to what you are saying, if the earth is attracting the stone towards itself, then the stone also should have attracted the earth towards itself, because that's what the universal law of gravitation says. Well, my dear students, my answer to this is yes. The earth is also attracted towards the stone. The only problem is the mass of the earth is so humongous that when it moves towards the stone, the movement is so subtle, so small, that we cannot actually see that movement with naked eyes. In fact, compare the mass of earth with that of the mass of a stone, which is barely 1 kg. If you think about a stone of 1 kg also, think about the mass which is of around 10 to the power 24 kgs. It's 6 into 10 to the power 24 kgs. If I consider that, what do we find? We find that the attraction would be there, but the visible displacement or the visible movement of the earth towards the stone cannot be seen. So, though the various objects on this earth attract each other constantly, they do not cause any motion, because the gravitational force of attraction between them is very small. It is, this gravitational force is it's so small that the movement actually cannot be seen. It is, something which is unobserved. But yes, if you throw a stone towards the earth, you can see it because of the difference of masses. Going down with the flow, I'll take up a small question over here to explain this concept more clearly. If you see, there is a question which is given over there, a sample problem. It says calculate the gravitation due to Earth on a ball of 1 kg mass lying on a ground. And the information that we had been provided regarding the mass of Earth, it is 6 into 10 to the power 24 kgs. The radius of the Earth is 6.4 into 10 to the power 3 kilometer, and the acceleration due to gravity, for the simplicity of calculation, we have taken it to be 6.7. My dear students, there are people who make a mistake. They say somewhere, sir, you are saying 6.67, and somewhere it's written as 6.7. Well, my dear students, this is a numerical. Numerical can have any value, but you need to stick down with the theoretical value, which is 6.67. We'll stick down with that 6.67 into 10 to the power minus 11 Newton meter square per kg square. But for this particular question, where we will be trying to calculate the force of gravitation, if we would find that we need to take 6.7 for the simplicity of calculation. This is something which is numerical dependent, nothing to do with actual value. For the simplicity of calculation, we might do this. But at the end of the day, the value is 6.67 into 10 to the power minus 11 Newton meter square per kg square. Check with this. We are asked to find the force of gravitation. So F is to be found out. We use the same formula that we had been discussing at length till now. If I use this formula, I have all the values being provided to me. All the values are provided to me. M1, which is the mass of the Earth. M1 is the mass of the Earth, which is found out to be what, or rather given in the question as what? It it is given to be 6 into 10 to the power 24 kg. The mass of the ball, which is M2, is taken to be what? M2 is taken to be 1 kg. Now, what we can have a value of, the value of G. The value of gravitational constant G is taken to be 6.7 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Got it? And if you see the radius of the earth, when I'm talking about the radius of the radius of the earth is taken to be the distance between the two bodies, and it is what? 6.4 into 10 to the power 3 kilometer. What we can do over here is we can convert this into the SI system, which is the meter. So it would be 6.4 into 10 to the power 6 meter. If we put all these values over here, we would find the value of F is coming to be 9.8 newtons, a value which is which you people are very closely associated with it. You must have seen this value time and again. F is equal to 9.8 meter plus 9.8 newtons. Kg would be having what? It will be newtons, the unit of force. When two objects or bodies are very big, having very large masses, then the gravitational force of attraction between them becomes very large. Because in that case, what happens? The bigger values are being dealt with. Then it won't be 1 kg, it would be comparable masses. Since the masses would be comparable, since the distance would be huge, as a result, the calculations will show that the force it would be much, much more when it is the attraction between the sun and the earth, or the moon and the earth. It will be something like that. We have a second question coming your way. Would you like to have a glance at this? Let this be the last question before I take up questions. Take up questions for this session. What do we have? The mass of the Earth is taken to be 6.6 into 10 to the power 24 kg. 6 into 10 to the power 24 kg. The uh, mass of the Moon is taken to be 7.4 into 10 to the power 22 kg. The distance between the Earth and the Moon is found to be 3.84 into 10 to the power 5 kilometer. So if it is 10 to the power 5 kilometer, we can easily convert that into meters. 3.84 into 10 to the power 8 meter. The value of G is also provided to you, which is 6.7 into 10 to the power minus 11 Newton meter square kg to the power minus 2. My dear students, please fill this up in the formula that we have and check, and then check what is the force that is exerted between the earth and the moon. Let's do it fast. Once we complete this, then what we'll be doing is we'll be shifting to the discussion of the questions that you people are trying to put forward by raising your hand. We'll address those questions. It's a simple one. We put over here whatever values we have got. We have G. The value of G is 6.7 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Isn't that what we have? We just put that value of G over here. What is the value of M1? The value of M1 is 6 into 10 to the power 24, whereas the mass of the moon is taken to be what? The mass of the moon is taken to be, or rather provided to us as what? It is provided to us as 7.4 into 10 to the power 22 kg. Got it? 7.2 into 10 to the power 24 kg. And the value of the distance, that is r, between the two bodies, the earth and the moon, is 3.84 into 10 to the power 8 meter. Remember, need to convert it into meters. When we put all these values, we are getting a value of force of attraction between the two bodies to be 2.01 into 10 to the power 20 meters. Please calculate this fast. We just have a minute to go for this. Complete this. check on with the exponent part of 10. Check over here, it should be 10 to the power minus 11. I'm not even concerned about what are the magnitude. I'm just going for the for the exponent, but 10 to the power minus 11. You have 10 to the power 24 over here. You have 10 to the power 22 over here, isn't it? 10 to the power minus 11, 10 to the power 24, 10 to the power 22. That makes it 24 plus 22 is 46. 46 minus 11. What is
35.
46 minus 11?
35.
It's 35.
35.
10 to the power minus 35. And if you check what we have over here, 10 to the power 16, right? When the 16 goes up, 35 minus 16, it would be around 19.
19. Wow,
Now,
yeah.
if we do all these calculations, you'll be finding the value to be 2.01 10 to the power 20 newtons.
So,
I expect that we all have completed till this portion.
yes.
Right. So let me stop the sharing of the screen, stop the recording, and then take up the question.